Hello everyone, welcome back. This is lesson number 2 continued. We're talking about limits graphically. In the very first lesson, we talked about continuity, what it means to be continuous at a certain value, and then the types of discontinuity. In this video, it's just practice, practice, practice. We're going to do a lot of practice examples and hopefully reiterate what we talked about in video number 1. So for question number 1, it says, for the following graphs, determine if the function is continuous at the marked point. If it's not continuous, explain why and describe the type of discontinuity. So we have 5 examples here, and the first one is at x equals -1. So hopefully you guys can see, remember the definition of continuity is that the limit as x approaches some value of, let's say, c of f of x has to equal whatever f of c is. Okay, so the limit approaching c of a function must be equal to where it's defined. So another way of thinking about continuity is if I were to trace my graph, I don't have to actually pick up my pencil or my pen in order to keep tracing it. Well, here I have to pick up my pencil and then start going down here. So I know it's not continuous at x equals -1, right? At x equals -1. So I can now say that this function has a jump discontinuity. And I know that based on the fact it's a piecewise function, right? It's just a jump discontinuity. And another distinguishable thing is that the left-hand limit, so the limit as x approaches -1 from the left of f of x, does not equal the limit as x approaches -1 from the right. All right, so those are all the things I can say about example number 1. All right, if I look at example number 2, I can say, again, I'm tracing, but oh wait, I have to fall in this hole per se, so I'm not continuous here either, because I can't trace over a hole. It's like you can't walk over a hole. So it's not continuous at x equals 3. And so since this is a hole, just like this is a piecewise function, we know that this is removable discontinuity. And the good thing about removable discontinuity that is different from the other types of discontinuity is that the limit, though, as x approaches 3 of f of x will exist. Right? It will exist. And it will exist at whatever this value here is, and we'll call that a. Right? So it's going to be equal to whatever a is. So there we go with that. So let's look at our next example. So again, we're going to trace, and we come up here to this peak, and we can keep going down like here. So we're good. So this is continuous as x is equal to 2. So we're happy with this problem. That means that we know that the limit as x approaches 2 of f of x, and that value is going to be whatever this y value is here. We'll call this b, and that's going to be equal to f of 2. And f of 2 is defined. It's defined at that point right there. All right. I know that there's a sharp corner here. That will be a discussion that we'll make a little bit later on in the course about what's going on there. All right. So example number D, we'll call it, is again, I'm tracing my graph, and all of a sudden I've got a brick wall. I have a brick wall. I got to climb over the brick wall to come back down. So I wasn't able to trace over it. So again, it's not continuous at x equals 2. And I can say that this one, because there's an asymptote there, it's infinite. It's an infinite discontinuity. And I can just say, like before, that the limits do not equal each other. And I can also say that f of 2 is not defined. Right? So I can go ahead and say that the limit as f approaches 2 from the left of f of x, even though they're technically positive infinity, right? But positive infinity does not equal positive infinity, so they do not equal each other. And I also know that f of 2 is not defined. And then our last example that we're going to do is going to be this one. And again, we're tracing. And just like before with number 3, or with part B, again, I fall into a hole. So this is exactly what you see in purple. It's not continuous at x equals 0. It's still removable. And so why do we have both these examples for you? Well, we want you guys to know that it's discontinuous. Is that even though we have a point here and we don't have a point here, so in this case, f of 0 is defined, right? F of 0 is defined. It looks like it's at the origin. Here, it's not defined, but it doesn't matter. All we're caring about right now is limits. All we care about now is limits and continuity. So even though it's defined, these are not equal to each other. So for this one, I can say that the limit as x approaches 3 of f of x does not equal f of 3. Okay, so that's kind of the idea behind that one. All right, so hopefully those make sense to you guys, and we are good to go with that problem. All right, so let's move on to example number 2. So question number 2 is extremely easy if you know the definition of continuity. It says suppose that f is continuous at x equals 3 and f of 3 is equal to negative 5. All right, so the first thing we know here is that f is continuous at x equals 3. So if we know the definition of continuity, then we know that f of 3 is equal to the limit as x approaches 3 of f of x. That is the definition of continuity. It tells me that my limit exists, and it also tells me that my function is defined at that same value. Well, if I know that f of 3 is negative 5, then I know that if this is equal to negative 5, then by the transitive property, we know that this limit is also equal to negative 5. So I know that this limit as x approaches 3 of f of x is actually equal to negative 5. And we can justify our answer by saying that by the definition of continuity, so this is the definition of continuity, right? By the definition of continuity, I can now say that f of 3 must equal this limit, right? It has to equal it. Therefore, this limit has to equal negative 5. All right, so again, definition of continuity really helps us with that problem. So let's look at this next example. Suppose that f is not continuous at x equals 2. So the first thing I can say on my paper is that f of 2 does not equal the limit as x approaches 2 of f of x. Because again, if it were continuous, this statement would be true. So I can immediately say that. Well, I now know that this overall limit here, this right-hand side, is actually equal to 25. So indicate which of the following statements of f must be true, which might be true, and which cannot be true, and justify your answer. So I know that it's not continuous, right? So it says, is f of x exist or x equals 2 is in the domain of f. So this means is f of x or is f of 2 defined? Well, this could sometimes be true. This is sometimes. Even though my limit exists, right? So my limit is actually equal to 25. So at x equals 2, and we're just going to assume this is 25, I have a limit, right? So I know this is true. However, I could have a point that's right here, right? And this is going to be, we'll call this now c. So f of c, or f of 2 in this case, would be equal to c. I don't need this point, right? So this goes back to the conversation that we had earlier where, okay, here my limit exists, and let's say this is now 25. And so it's not defined, so this is the case where it's not defined. And let's say that this is 25. So my limit exists here at 25, but also it's defined at 0. So sometimes yes, sometimes no. And so those were the two examples for that. So this is sometimes. This is sometimes. Is f of 2 equal to 25? Well, I clearly know that this cannot be true. This is never true. Because if these are not equal to each other, so if f of 2 does not equal to the limit as x approaches 2 of f of x, right? And I know that the limit as x approaches 2 of f of x is equal to 25, and these are not equal to each other, then this cannot equal 25, ever. And then lastly, the left-hand limit is equal to 25. Well, we talked about this before, that if the right-hand limit is equal to the left-hand limit, then I can say the overall limit exists. And then I also know that all of these are equal to the same value. So if this is equal to 25, I can also say with certainty that this is also going to be equal to 25. So the answer is true. Or always. I should say always. Always. All right. So hopefully that's okay for everybody. Example number 4. Example number 4 is just basic, simple limit kind of stuff. So for number 4, it says the limit as x approaches negative 5 of f of x. I'm not going to spend too much time on this. So if we're going to negative 5, right? The limit is we're going to -5. We come up here to our function, and what are we approaching? We're approaching 4, right? We're getting close to 4, because remember the limit notation, as x approaches some value in the x direction, right? X direction, so x approaches -5. What's my function doing? Where's my function going? So as x approaches -5, so I'm at -2 now, I'm at -3, I'm at -4, at -5. What's my function doing? It's approaching what y value? And it's approaching 4, right? It's approaching approaching 4. So that's how we do that problem right here. As x approaches 0, right? So for part B, as x approaches 0, well, let's look at that one. Well, as we approach it from the left-hand side, we know that this value is 0. As we approach it from the right-hand side, we know this value is 8. Since they're not equal to each other, we know that this does not exist. All right, does not exist. What about if we look at x equals 2, right? If we look at x equals 2, well, again, from the left, it's approaching 3. From the right, it's also approaching 3. We've had this conversation already now. It doesn't matter that it's open. We know that it's a removable discontinuity. That's great, but removable discontinuity means that the limit does exist, and the limit actually is equal to 3. All right, and then the last one that we're going to look at is 4. As x approaches 4, and for 4, again, from the left, we're approaching 0. From the right, we're approaching 0, so the answer here is 0. So like I said, just pretty straightforward, simple questions for us to practice these problems. So hopefully that is all making sense to you guys. Let's continue. So example number 5 does a really good summary of graphics with limits and discontinuity. So if you guys look at A through E here, we're all about 0. We're all talking about 0 for this. So I encourage you guys to pause the video, look at it, see what you guys can do with the problems, and then we'll come back and talk about it. And then for questions F through H, we talk about 1, what's happening at 1, and then I, we're talking about what's happening at 3, right? What's happening at 3. So if we're looking at 0 from the left, so this is 0, and notice that these are 2, so H, at least these tick marks are 1, so this is 1, so this would also be -1, so just be careful with these kind of things when we're looking at our values, so you want to be really careful about how the markers work. So I'm going to go ahead and just really highlight these numbers for us. So as x approaches 0 from the left, right, so 0 from the left, then we're going to get that this value is going to be -1. So we're approaching 0 on this graph from the left. If I'm approaching 0 from the right, then I'm hitting the graph here at 0. And since these two numbers are not equal to each other, then I can say that this overall limit does not exist. I also can say that there's no closed circles here. There's no points that's defined here. So this is open. So f of 0 is also undefined. And we now know that is this function continuous at x equals 0? And if not, tell the type of discontinuity. Well, you guys remember from the first video that we're literally walking along, and then all of a sudden we have to jump up, right? It's a piecewise function because of the hole. We have to jump up, so that is going to be jump discontinuity. Okay, jump discontinuity. Okay, so let's look at x equals 1. So we're here, this little guy. And again, ladies and gentlemen, this is just kind of review. You can see that 1 to the left, right? 1 to the left, we're approaching 2. 1 to the right, we're also approaching 2. The overall limit is also 2. Because these two limits are equal to each other, we know that this is equal. F of 1 is actually equal to 1. And so we now know, is the function continuous at x equals 1? Well, the answer is no, because again, in order for it to be continuous, f of 1 has to equal the overall limit. So this little guy right here, right, has to equal this guy right there, and they're not equal to each other. So it's no, and we can say that this is a removable discontinuity. And again, you guys remember that removable discontinuity is because there's a hole right there, right? There's a hole in the graph. And the last one is going to be I, and it's right here for us, and it's going to ask us about 3 from the left, the right, and up. So 3 from the left is going to end up being 0, right? So we're approaching 3 from the left, which is 0. We can say 3 from the right, 3 from the right is going to be all the way up, 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 and beyond to positive infinity. And then, since these are obviously not equal to each other, this is going to be does not exist. And we can now say that there's an asymptote here. So I know that this one is going to be no, it's not continuous, and it's because it is infinite. And remember, you can also write asymptotic here for discontinuity. So there we go with that problem. So hopefully that is making sense to you guys. These, example number 6, we're just going to really quickly go over. I don't feel like you need to see this one too much. So for question 6, look at the graph below. So 2 to the left. So we're looking at 2, which is right here. So to the left is going to be this y value right here, which is going to be equal to 3. 2 to the right is going to be this y value right here, which is going to be 1. So clearly this limit will not exist because the left and right hand limits are not equal to each other. 5, so this is going to be at 5. We know that this limit's going to exist without doing the problem because we know this is a removable discontinuity. We can see that in the graph that there's a hole here. I do not care about this point, so I know that both left and right end up being at this value here, which is 2. So this is 2, and therefore this is 2. So that's probably one of the fastest examples that I was going to do with you guys. And to finish up the video, it says write the limit statements. So we're going to write the limit statements and values for x equals -2, 0, and +2. So at x equals -2, so we're going to write the limit as x approaches -2. And because there's is a piecewise function, we want to write a left-hand limit and a right-hand limit. So x approaches 2 from the left of f of x is going to be equal to, well, again, we don't care what's happening all crazy over here. We really care about, as we're traveling along a road, as a road here, we're trying to get to this value right here, right? And that value is going to be, well, what's to the left-hand side? Well, as we're approaching our graph, once we get to -2 from the left, well, we're approaching the y value of 1. The limit as x approaches 2 from the right, and again, look at the notation to make sure you guys are good with that. If I'm approaching it from the right, put a little plus on there, right? So now I'm following along my trail here, my function, and so I'm going to go this, and this is going to be equal to 0. And so I automatically know that my overall limit for f equals, these all should be negative, by the way, I just realized that, -2 does not exist. And again, because these two numbers are not equal to each other. So hopefully that this is all making sense to you guys, because like I said, we've done quite a bit of examples of it. So let's look at the next one. So let's look at 0. So the limit as x approaches 0 from the left, we're going to go ahead and do all of them, right? So from the left of f of x, so we're approaching 0 from the left this way, we're going to hit 1. We're going to look at the limit as x approaches 0 from the right of f of x, and that is going to be this way. It's also going to be 1. Therefore, I can now say that the limit as x approaches 0 total, the overall function, is also going to be equal to 1 because they're equal to each other. So that is a very easy, straightforward one. And then finally, ladies and gentlemen, the last one of the lesson, we can see that x equals 2, and it's going to be the same story as -2, right? Because it's a jump discontinuity. There's a piecewise function. We have to write both the left-hand limit, we have to write the right-hand limit, and we already know from the fact that we know what discontinuity looks like. We know that this is a jump discontinuity, so we automatically know without looking at this that this overall limit is not going to exist, right? Because the left-hand and right-hand limits are not equal to each other. Where our left-hand limit, again, is where we're approaching from the left, and so this y value is going to be 0. And we're looking at from the right, and this y value is going to be 3. And so, again, these are not equal to each other. We already knew this wasn't going to be equal to each other, so we know the limit does not exist. So that is lesson number 2. I hope that this makes sense to you guys. Like I said, this video was very, very fast, right? Because I was just doing practice problems and showing you guys what to do. So good luck, and I'll see you guys in video number 3.